Okay, minasan konnichiwa, Samurai Engineer desu. So in this segment, we will continue our discussion of example 1. Okay, please sound check.
Because minor imperfections in materials, they measure minimally in although in computation, we have a very simplistic computation that's meaning of how to design, how to analyze a column. Our complex design and analysis is therefore a big body state. Column is more a more critical member than a big. This part can be illustrated by a bridge truss that has some of its members damaged by a truck.
Please sound check.
Let's imagine a truss damaged by a truck. The bending of tension members probably will not be serious, as the tensile loads will tend to strengthen those members.
Okay, thank you. Thank you. Shout out, Daniela. Okay, let's go back to example number 1. We already found out the values of the properties of W section using AISC table. Now, if your table is like this, again, meaning your table is not complete, your table is an abridged version, okay? So this is your table. It is not complete. So as you can see, you have what? You have this W 10 by 30, okay? Okay, so you have there 10 by 30 and 10 by 12, but you need to look for 10 by 22. Again, we are going to interpolate the value. So this is for RY, okay? So as you can see here, we show you RY, okay? This is for RX, so RY, RX. So let's go back to that. So this is RY, this is RX, and this is the area. So I will just give you an example of one interpolation. You can do the others, right? I will do the RY interpolation, do the RX, and do the area interpolation. Okay. So I will show you my calculator.
We want every space to be utilized. Follow by that we visually beautiful.
Okay. So let's show you my calculator.
Put on the proper size, dimension,
Okay.
position. As an economic and detailed study by John Brody indicates that when shallow spread footings are used, not shallow spread footings.
So for 30, we have our
Led to with ratios of about 1.25 to
30.
1.25.
Okay, so here
1,000 square feet are the most cost efficient. Take note of that.
we have 30 and 12. So we need 22. So therefore, let us have 30 minus 22. We want to find out the value of Ry for 22. So I am solving for Ry, interpolation. You have to solve for Rx and for area. Okay. So it is divided by 30 minus 12. Okay. What is this ratio? This is the ratio given from table. This is what you want. This is given from table, maximum. This is given from table, minimum. Where is that? Here. Maximum is 30 and 12, minimum. So that is the range of minimum, maximum. That includes your desired value. Our desired value is 22. These values includes our 22. Okay, meaning 22 is inside, in between 12 and 30. Okay? So let us use equals. Then what is 1.37 is Ry. So 1.37 minus what? X. So let us use X because we do not know. We do not know the value. That's why we are going to use X. And then maximum is 1.37 again. Minus how much? That's 0.8 to how much? 0.785. 0.785. Okay? So if you have this, then we have to shift solve. Okay? Shift solve. Okay? Why this is negative? I don't know. Why we have shift solve negative? Why the answer is negative? 1.3. Can we... So the answer is 1.33. But why it is negative? Okay. So why it is negative? We have the correct answer. 1.33 is the requirement, but our answer is 1.3. Okay? So our answer is 1.3, but our answer is negative. So why it became negative? Okay? Let us clarify it.
Residual expressions and distribution of the important factors. These are particular forecast components with slenderness ratios varying from 40 to 120. Slenderness ratio meaning length divided by R or reduction by 10 ratio. So
Divide
to 120 range that includes a very large percentage of practical columns. Practical columns in practice.
I think this is correct. This is correct. Why it is negative? Why it becomes negative? Shift solve or value of X.
So the stress is retained inside the material. For instance,
1.11. Okay. 1.11. Okay. Is the computed value, sir. Okay. So 1.11. 1.11. Okay. So I also have 1.11.
for the data of interaction.
Why it initially show 1.3? Negative 1.3. What happened?
The intersection of the class
Initially it shows negative 1.3.
that is logical and PSPE.
Then now it shows 1.11. Okay? The answer is 1.11.
Studies.
What happened?
Always there's a pressure. So
Right.
residual stresses.
So anyway, that is the procedure. The way we have to do the interpolation using calculator. Okay. I don't know what happened here. Our procedure is correct, so we will stick to that. So anyway, 1.11 here, but it is supposed to be 1.33. So we have error of about 0.2. We have error of 0.2. Okay, 0.2. So what is 0.2? How much is our error? 0.2 divide 1.37.
Sample sections of column
What is this? What's happening? What's happening in my calculator?
Regular section, C channel, regular section, W section is regular one, pipe or round, HSS to be regular section.
0.2
HSS regular,
divided by
HSS
1.33 is our error. How much is our error?
This is a build-up.
It's very large. This is a large error.
Use
Okay, so I think this would result in a very large error. Okay, this is 16% error, and therefore you have to what? You have to better use the formula for finding out the I inertia, then divide by area. So inertia divide by area, then square root. Okay. So I will show you again. I will show you. That is possible. I will show you. Is there an inertia here? Inertia. Let's take a look. Inertia. Okay, so we have an inertia here. I will show you. Okay, for example, here, we have an inertia 757. Okay. And okay. And then we have an area 62.2. So I will show you. Inertia, which is 757 divided by area, which is shown a while ago to be 62.2. 62.2. Okay. Okay. So 62.2 divide. So you have this area, this quotient. Then take the square root of this. Take the square root, and the answer would be the value of R. Take a look. 3.4886. So the value of R in your table is 3.
Meaning we have a W
49. So that is equal.
A C channel on the upper class and
So that is equal.
lower class. Right? So that's why it's called double. Then channel.
Wait. What happened?
Welcome section. Looks like I mean, but
What happened in my window?
Angles 1, 3, 4. So the 4 angles
Duck.
will function as slats and then provide the web. Okay, use a plane to function as a web.
What happened?
Another built-up section.
I don't know what's happening.
Similar to this one, but you have another plane, tab, and photo plans. Okay, so those are
Sin.
the types of columns, types of cross-sectional level column. Okay, so you have to expect any one of that, and you can use any one of that. Okay.
Transition sin.
In our design, we will just take a look at the regular sections that we
What
built up.
happened?
So when you put this built-up section, it is you can analyze it as we are analyzing the.
I have a problem in my ano. I have a problem here. I can see my screen.
So as you can see, we have the steel columns on beside our stool. We
I can see my screen. Why?
We have walkways with the steel column that are circular, and that is like this. NSS, 5 SSS, like this. It's column steel, 5 round NSS tubing. Column, okay? Steel column.
Cannot see my screen.
They have mounted on the reinforced concrete short column. As you can see, along the side of the university.
Can you confirm? Do you see my calculator and my camera? Do you see my cam and my calculator?
So next topic are the development of column formulas. We already talked about this from the theoretical point of view.
No, sir. Wala po, sir. Sir, di na po kita. Calculator, what about calculator?
Textbook explanation.
No, sir.
Textbook explanation.
What happened? Please give me 30 seconds.
Test result record when testing by N over R is the independent variable and PU over A is the dependent variable. Testing several points, several specimens. The testing results have the dots, and then we have to represent those dots into
What happened in my...
This is the curve of the mathematical equation that represents all these dots. Okay? That's why it is not precise. Okay? Just that it is not very
what happened?
as you can see. So, really, the Euler formula is the basis of so many things with respect to compression effects. Okay? So, obviously, the stress and
Preview. Where is my preview screen?
as the column becomes longer. That is quite logical. It is easily
What happened? What happened? What's happening?
fail if the column is low. Okay. So for a column to travel elastically, it will have to be long and selected. Its buckling load V can be calculated using formula that follows. So as you can
Settings.
recall from last week, we have the curve. We
Hi.
the Euler value load V with respect to the ideal. And Euler load V is the maximum. Is the maximum. Okay. And that is equal to pi squared EI over L squared. Okay. This formula usually is listed to the form that involves the columns and representation. So take out again, just like what I said, is the definition of
General output
right. So divide both sides by A,
projectors
right?
preview.
The Euler buckling stress. So this is the buckling stress. Okay. This is now for what? This is what we use for global
Preview.
buckling.
What happened
We use for global buckling.
with that preview?
So global, flexural, and Euler formula. We have the next one, which is local buckling and torsional. So those are the main modes.
Transition to scene when double click.
So again, please familiarize yourself, even better memorize these formulas. Okay, let's
So what's happening?
go to the examples. Example 1. So we are going to determine the column's critical or buckling load.
Oh my goodness.
Okay, if we are given W10 by 22, okay, used as 15 feet long pin connected column. Pin connected. Take out. If you consider the connection, there is what we call K factor, right? And the K factor
Casio.
is equal to 1 if the column has pin connection. Recall,
Casio is
as
off.
meaning, okay? Assume that this still has a proportional limit of 36 PSI, so the 36 material. Okay? And determine repeat part A, the length is changed to repeat. So let us compare if really the length of the column will affect influence the susceptibility of the domain. Okay, so let us solve problem solution 3 using big data.
Okay, can you see the calculator now?
Let us
Can you see the calculator?
table W10 by 22. We have W10 by 22. W10.
Do you see calculator at the center or at the side?
W10.
The center or at the side? Or at the right side?
Okay, then W10 by 30.
At right side.
W10 by 12. You can use interpolation. You can use W10 22. You can use interpolation. Interpolate 30 and 12. Right? Interpolate it. Okay? You have to use interpolation between this. Or you can use a better table which has W10 by 22. So let us find out. W10 by 22.
Right side po. Okay. So, right side.
By 22. So we have
Okay, sige.
W10 by 22.
Let's
Okay, so
try.
W10 by 22.
Can you see my video? My video cam? Can you see my video cam?
10 by 22. What do you do that? Area there. Okay. So what are the important things that we need to know? Area. The radius of gyration x and radius of gyration y. Okay? So Rx, R1. So those are important. Area, Rx, R1.
Okay. So meaning
That is for
very slow, no? Very slow. So initially
as
you don't see it, but later
area or this area.
you can see the video cam.
Column is
Okay. Anyway, let's just continue. Let's see your feedback. Time in again. So listen for me.
So we have R.
Okay. Anyway, as I was saying,
Rx is
we can find the value of R by just using the inertia. Okay. By just using the inertia
this is 22.
part.
22. That is our
Okay.
10 by 22. So Rx is
What's happening?
4.91. Ito, 4.91. Ry is
What's happening? Okay. So use the inertia, then divide by area, then square root. You can find out there. The same is true with this Rx. This Rx, use the inertia 10,300 divide by A, and then the result, take the square root. You can get the R. Okay? So there are several ways. So if you do not have the correct table, okay? So what do you mean by this? Average. Okay? Average meaning summary. So summarize, not complete. It is not a complete. It is not a complete list because it is an average. Okay? So meaning there are several items that are missing. That is what we mean by average. Okay? So use interpolation. You do not have any way to calculate. Use interpolation, calculate and check with other method. So there are other methods. So you have to check it. If you are getting correct answer. There are no way. There are no other ways. Okay? I am showing you different ways so that you can check and recheck. Okay. So let's go back to the example. So we have minimum R. Okay. Which one is the minimum? 1.33. So Ry. Because we are in column, Ry will be the weaker link than 4.27. So 1.33 is weaker. So we have Ry. So therefore, use 1.33.
Let us verify.
Because smaller value of this will give us a larger ratio. So the smaller ratio, we want the larger ratio because the larger ratio here would be critical for failure. So the larger L to R ratio. 15 foot length of column divided by 1.33. then convert into inches. The answer is 135. Okay. So use this value in our determination of Euler buckling stress. Okay. So this is our stress. Okay. So what is the value? 15.63. Okay. This 15.63 stress is less than the 36, no? Value of stress that could be handled by the material. So therefore, it is okay because the material strength is 36, the stress is just 15. So it's okay. So elastic or buckling load. So just multiply by the area. So the area is again here 6.49. So multiply. So our load is 101.4. Okay. So that is supposed to be the maximum. Don't equate this stress to the capacity of the material because Euler stress is maximum. Euler stress is already maximum. This is already maximum capability of the material. Although we are checking that this is less than the proportional limit of this one. While we know that this is less than proportional limit because this is less than 1/2. 1/2 of 36 is what? 18. Oh. Take note, we have that in our concept, in our principle. Okay? So that is still within the proportional limit. Okay? Okay? So letter B, what about if the length is 8 feet rather than 15? The same material, the same section, but now we are using 8 feet. So 8 divided by 1.33, 72.18. So a while ago, we have 135. Then, okay. You do not see it. Okay, so this is letter B. We are using 8 feet long rather than 15. So now, 8 feet divided by 133 multiplied by conversion factor, 72. So a while ago, we have what? 135. So compare this one to this one. This is 15 feet, this is 8 feet. Okay? So using the same formula, but now you are using the ratio. Okay? 72.18. So what is the value? Okay? The value is now 54.9, which is greater than 36. So the column is in elastic range. Inelastic. What do we mean inelastic? In the plastic, no? We are now going to the plastic. So because we have two regions, elastic and plastic. Okay? So we have now the Euler equation is not applicable because Euler equation is in elastic region, not in plastic region. Okay? That's why we cannot choose that formula. Okay? So that means really we need what? Take note. 8 feet. Okay? 15 feet is okay. 15 feet is okay. But 8 feet, we don't know if this is okay. But the Euler equation is not applicable. Okay? So we have what? Because the ratio is on the denominator. The ratio is on the denominator. The ratio is on the denominator. We want large value here so that the stress is smaller. Because this denominator, the large value of denominator, we have smaller answer. Small denominator, we have bigger answer. So larger answer. Okay. So that is for example 1. The student should carefully note that the buckling load determined from the Euler equation is independent of the strength of the steel used. So independent. Okay. So that's why I explained to you that Euler is the maximum. Okay. The Euler equation is useful only if the end support conditions are carefully considered. Okay. The results obtained by the application of the formula to specific examples compare very well with test result for concentrically loaded long slender columns with pin ends, pin connection. Okay. Because K is equal to 1. Supposed to be KL over R when we consider the type of end connection. Designers, however, do not encounter perfect columns of this type. The columns with which they work do not have pin ends and are not free to rotate because their ends are bolted or welded to other members. These practical columns have different amounts of restraint against rotation, right? Varying from a slight restraint to almost a fixed condition. And for actual cases encountered in practice where the ends are not free to rotate, different length values can be used in the formula and more realistic buckling stresses will be obtained. Okay? So this is really just a theoretical because pin connection do not really happen in actual. Okay? Okay? Only in theory. Only in discussion just to express the description of the Euler formula, how it works, how it will affect. Okay. Other than that, pure theoretical. Okay. To successfully use the Euler equation for practical columns, the value of L should be the distance between the points of inflection. So meaning we need to put in the K factor. Okay. So because not only the length, but we have to use the effective length. Okay. So effective lengths due to end restraint. So there are several types of that. Okay. KL is the effective length, where K is the effective length factor. Okay. What about this? Here, you have to memorize. You have to memorize this. Okay. If you are seeing this type, that is what? Pin connection. So K is equal to 1. The factor is equal to 1 here. K is equal to 1. If you see fixed on both ends, K is equal to 0.5. Here, 0.5. And if fixed in one end, pin on the other end, 0.7. K is equal to 0.7. Okay? So therefore, the effective length is 0.7 L. Effective length here is 0.5 L. Effective length is L. Okay? So you have to use those situation and what? Again, there are so many tabulated values for K. So you cannot memorize them all. What is important is the description that K represents the inflection to inflection distance. Okay? Inflection to inflection. So therefore, you can use what? Calculus. Because you, what is the inflection in calculus? It's the second derivative. Take the second derivative. You can have the inflection points. Okay? Second derivative. So take note. That is now your responsibility. Use calculus in order to find the exact value of K given the endpoints. What do you need to do? Given the endpoint, then use the structural theory, and then you have what? An equation. then take the second derivative so that you can find out the distance from inflection point to another inflection point. If you take the second derivative, you can get the value of inflection point. You can get the location. So after locating the inflection point, then find out the distance. Distance of one inflection point to the other inflection point. Then after that, use that as equal to the value of k. That is the k factor, the distance. That okay. Or if your unit is already in linear meter or linear foot, that distance is actually the effective length. Okay. So if your unit is dimensionless, that is k factor. Okay. So this is a figure representing 1/2, no? K is equal to 1/2. So this is the total inflection from this point to that point. So from this point to this point, that is only 1/2. Column is in position, lateral deflection. So L. Okay. Again, another table. So you can find so many tables with effective length factor K. So fix. Again, fix. We know that is 0.5. One end is fixed, one end is pin, 0.7. Okay. So one end is fixed, the other is free to move, 1. Both are pin connection, 1. One is fixed, the other is pin and can move, that is 2. One end is pin, the other is fixed but can move, that is also 2. Okay, so these are actually so this looks like what, 2. Okay, that looks like a 2. So it looks like a 2, not 1/2. So sorry about that. Okay, so 1/2 is like this. This is 1/2 because this is from this point, from the inflection to that point, that is 1/4. From inflection to that point, that is 1/4. So 1/4, 1/4, 1/2. Okay. But anyway, although you have this theoretical value of k, practical value, in actual, you are actually using this. Recommended design value. 0.5, use 0.65. 0.7, use 0.8. 1, 1.2. 1, 1, 2, 2.1. 2, 2. Okay? In condition, rotation fixed, translation fixed. Rotation free, translation fixed. These are the symbols, right? So, rotation could be fixed, but translation fixed. Meaning, free to move, translation. Can move from 1. So, this is translation. These are the translation, okay? Translation. 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 Movement, right? Those are the value of k, and therefore use them for solving the equation, particularly in solving Euler stress. You can use effective length divided by radius of gyration. Okay, 5.7 stiffened and unstiffened elements. So stiffened elements here. So unstiffened elements, just welding. So T section. Unstiffened elements again, just bolted here. Hi. Hi. Another unstiffened elements here. Okay, flange bolted on another plate. So the flange is bolted with another plate. Take note, stiffened elements. Okay. So we have this one. So you are looking at the web here. So stiffened with welding and plate. So we have this welds and plate. Compare that to this one. Also this one. Compare this to this one. Okay. So stiffened. Okay. Almost the same. Almost the same. Okay, almost the same. What about the next one? This one. So stiffened elements. So we have this one. Plate and then welded. So we have section, W section and plate. Another one. Stiffened elements. So built up section. Oh, this is built up section, built up. They are built up section. Okay. Ate. Ate, where is ate? Where is ate? Where is ate? Bagal naman. Bagal naman. Tissue. Okay. Hi. Let's go. Let's go on. Where is table 5.2 and table B4? Where are the tables? Where are the tables? So table 5.2 width to thickness ratio. Okay. So very important table, width to thickness ratio. Okay. So case 1. Okay, case 1. So how many cases are there? So this is case 1. Let's look. Case 2. Then case 3. Case 3. Case 2. Case 3. Then case 4. Then case 5, case 6, 7, and 9. So, okay. So, to 9. So, let us take a look one by one. Cases. This table is for what? Width to thickness ratio. Okay. What do we need? We need the values for B and T because width to thickness ratio. Okay? That's why we have here a different what? Look at B. B. Right? Stiffened because this B is strong. If you have this, additional is not stiffened element. Okay? But here, this stiffened element. So this is stiffened element. Stiffened. So take note of B. Because we need B divided by T. Take note, B divided by T. That is what we mean by this, no? That's why I am looking for table 5.2 here, no? B divided by T, okay? So, which means, okay, plans of rolled I-shaped section, plates projecting from rolled I-shaped sections, outstanding legs of pairs of angles connected with continuous contact, plans of channels, and plans of teeth. Okay? Plans of channels, plans of teeth. So, every plans, okay, like this, no? Like this, as shown. Sample. B divided by T. That is width to thickness ratio. Okay, width. Okay, T section width. Channel, C channel width. Take note the communality of this. These are just one half of the flans. Okay, so this is about one half. This C channel looks like this, no? One half of W section looks like C channel. T, one half of this. So from the center to the edge, that is what we call B. So it differs when we are looking at this concept. It is different from the normal value of B, the width. The normal value of width is from edge to edge. Okay? From edge to edge. Not this one. This one is B, okay? But this one is not. The normal value of B is from edge to edge. But when we are going to use this table, so this table for Euler, okay? So we need to use the center to the edge. So what about this one? Again, from this to this point. So that is B. Okay? Okay? Any question? That is how we are going to use B. What about T? The T is usually the flange. Okay? T is usually the flange. But here, take a look. This is not the flange. Okay? Oh, this is not the flange. In the built-up section, the thickness is there. So this thickness is different from this. So usually the flange thickness here, here, here. Again, take note. This is different. Okay. Case number 2. Okay. So flange of built-up I shape. So built up. I think this is also flange of rolled I shape. Rolled meaning it is not built up. Okay? It is a regular shape. But take a look. How can we have this rolled? So this is this part is built up, but this is rolled. Okay, this part. Okay, I don't think there is no rolling of this in the manufacturing. There is no rolling of this the manufacturing side. So while here built up. So built up meaning there are 3 plates that we have to connect to make a section similar to this one. So we have again 3 parts, then 1 angular. So connect the 1 angle here, built up. So what do we mean by B? B again, one half the plans. B is from the corner to the edge of the angle. Okay? And T is usually the plans, but here that is the angle. Okay? And take note of the formula. 0.56 square root of E over Fy. Okay? This is limiting. Width to thickness ratio. Limiting. So, this is the limit. Okay? Lambda R. So, non-slender and slender. Okay? So, this is the limiting value. Okay? So, between non-slender and slender. While on the case 2, 0.64. So, 0.58, 0.56, case 1, 0.64. But now, square root of KE over FY. So, we have KC rather. So, we have KC. Okay? Then, case number 3, legs of single angles, legs of double angles with separators and all other unsteepened elements. So, B over T, what do you mean by B? So, angle, the longer leg, that means the angle, longer leg, that is B. Okay? The longer leg, that is B. So, B is from the corner to the edge, then B is the longer leg, still the longer leg, that is B. Thickness is thickness of 1. Thickness of 1 angle element. Do not add the total thickness here. Okay? So, and the value is 0.45 square root of E over Fy. Okay? 0.45. Now, and number 4. Number 4, we have D over T. So, what is D? The depth. So, this is stem of T. That is the stem of T. So, D over... the limiting value. What is the limiting value? 0.75. E over Fy. Square root of that. Okay. Then, case number 5. Okay. Case number 5. Web of doubly symmetric I-shaped section. We have to look at the web. And the web height of the web divided by TW, thickness of the web. So height divided by thickness of the web. So case 5. What is the limiting value? 1.49 square root of E over Fy. So usually square root of E over Fy. That is the usual factor with numerical factor or coefficient. So there are different numerical coefficients here. Okay. So I section and C channel. Take a look. Corner to corner, that is H. Then thickness of web. So case 6. Walls of rectangular HSS and boxes of uniform thickness. So thickness of the wall, and then B is the longer distance inside what, corner to corner distance. Okay, so that is B over T. The coefficient is 1.4 square root of B over Fy. So square root of B over Fy. Only case 2 is different, no? Only case 2 is different. So for case 2, that is E over Fy, but we have KC. You have KC. Factor. Hi. And case number 7. Okay, case number 7. Take a look at the value of B and T. That is for K7, plans cover. So take a look. We have plans cover. So B is the flange cover width. Okay. Hi. If you are using bolt, then bolt to bolt distance. That is bolt to bolt distance. Cover, if you use welding, then the length of the cover. But if you use the bolt, that is bolt to bolt distance. Then thickness of that cover. Okay. So flange cover plates and diaphragm plates between lines of fasteners or wheels. Then case number 8, all other stated elements. Like this, regular shape. So B. So center to center of the thickness, then divide by thickness. 1.49. So this is 1.4 again, 1.49. Then square to B over Fy. Now this is different. E over Fy only, there is no square root. And then multiply by 0.11. For round shape, HSS, D capital T over T. So this is diameter. Outside diameter over thickness. Right? That is case 9. Okay? So these are the differences of the table. 0.56, 0.64, 0.45, 0.75, 1.49, 1.4, 1.4, 1.49, 1, then 0.11. Okay? Do you follow? So, usually B over T, B over T. Now we have D over T, lowercase d over T. Then we have capital T over T. Okay? So there are 3 types of columns. Okay? Long, short, intermediate. So actually long and short and intermediate is in between short and long. Okay? Okay? So when we talk about when we talk about the reinforced concrete column, we have what? Pedestal, short and long. There are 3 types. But when we are talking of steel, there are only 3 types also. Long, short, and intermediate. What do you mean by long? Euler formula predicts very well the strength of long columns where the axial buckling stress remains below the proportional limit. That is our example 1, letter A. Okay? Such column will buckle elastically. Okay? What about short columns? For very short columns, the failure stress will equal the yield stress and no buckling will occur. So yield. Okay? For a column to fall into this class, it would have to be so short as to have no practical application. Thus, no further reference is made to them here. So it is almost like pedestal. No practical application. Pedestal in reinforced concrete have very wide area of application. But when you are talking of steel, there is no practical application because why you have to, there's no reason for you to have a very short steel column. Reinforced concrete, very short reinforced concrete column. That is usable. Okay? Right? But for steel, that is not. What about intermediate column? Therefore, although there are three types, usually long column and intermediate. Okay? So for intermediate columns, some of the fibers, okay, will reach yield stress and some will not. So members will fail by both yielding and buckling. Their behavior is said to be inelastic. Most columns fall into this range. So there are many intermediate columns than long columns. Okay? For Euler formula to be applicable, okay, to such column, it would have to be modified according to the reduced modulus concept or to the tangent modulus concept to account for presence of residual stress. So usually, Euler formula is not applicable, but just like on example 1, 8 feet. 8 feet is a normal height of column. Oh, 8 to 10 feet. That is a normal height of column, 8 to 10 feet. 15 feet is a long column, but it is within the what? The Euler formula. But intermediate, without modifying, usually it do not belong to the Euler, but we have to what? Modify it, okay, to the reduced modulus concept or the tangent modulus concept to account for the presence of residual stresses. Okay, so column formulas. Okay, we already tackled this column formulas. We already know this when we talk about the manual. So at nominal force, nominal compressive force, FCR multiplied by AG or gross area. So now multiply by what? Compressive reduction factor, phi C, which is equal to 0.9. Okay. So for ASD, 0.9 is corresponding to 1.67 FCR. The following expressions show how FCR, the flexural buckling stress of a column, okay, flexural buckling stress, FCR, okay, will be determined for members without slender elements. Okay, so slender elements, those are usually long column. So the easiest column to design is long column. So if we have now within the intermediate column, therefore we need so many conditions. If KL over R is less than, so we already know this, last meeting, 4.71 square root of E over Fy, right? So FCR is supposed to be equal to this one, right? If this is the case, or Fy over Fe is less than 2.25. Okay? So if KL over R is greater than 4.71, so greater. So meaning to say, it is going nearer and nearer to slender element. So this is not slender column. This is not. So this is going nearer to the boundary for slender column because this ratio is greater than 4.71. Take note, again, square root of E over Fy. Okay? So FCR, or the flexural buckling stress, okay, FCR, flexural buckling stress. So flexural buckling stress is the one we need in order to calculate the design stress and the allowable strength. Allowable strength and design strength. Okay? So 0.877 FE. Okay? So FE is our elastic critical buckling stress. FE, elastic. So here, okay. So FE is the elastic critical buckling stress. Okay. So another formula here, FE is equal to critical buckling stress. Elastic. This is Euler. This is Euler formula. This is the modification. Rather than L over R, we have K. This is the modification. KL over R. Okay? Do you follow? So FE, then multiply by 0.877, so we have FCR. So FE is the Euler's elastic critical buckling stress. FCR is the flexural buckling stress. Okay? So here we only have to multiply Fy 0.658 exponent Fy over F. What is this? What is this from last meeting? Fy over Fr. Okay? Or Fy over Fe. I think this is Fr over Fe. Or Fy over Fe. So very, I cannot see. Very small. It's very small. Cannot see. But we have the formula last meeting. So you need to confirm to that video last meeting. Okay. So graph again, last meeting we already know about this graph. Similar graph last meeting. So we have the 134 for Fy is equal to 36. Okay, 113 for Fy, 50, and so on. So it depends on what type of steel you are using. Fy 36, 134. Fy 50, this is 113. So it depends. Point of tangency of curves. So curve number 1 and 2. So in elastic buckling, so this is elastic buckling. Elastic buckling, this is our Euler. So that is equation E3-3. In elastic buckling, that is equation E3-2. So refer back. So E3-3. So here, equation E3-3, equation E3-2. So this is right E3-3. This is elastic. Right? This is inelastic. Okay? And then Euler's. So always we need Euler's formula. Now modified, we have the K value. Okay, so take a look again. This is greater than what? 4.71. So this is equal to or less than 4.71. And this one. 4.71. 4.71 square root of that. Okay? That is 4 KL over R. So maximum slenderness ratio. What can we tell? After looking at this column equation, the reader might think that their use would be tedious and time-consuming with a pocket calculator. Such calculations, however, really have to be made because IISc manual provides computed values of critical stresses. Okay. That is practical, but in problem solving and in board exam, it is very limited amount of table will be given to you. Okay? That's why you need to know how to do it. Okay? Otherwise, if you don't know how to do it, you are what? A table engineer. You are always looking at the table. Okay? Tabulated value. So, and everybody can do that. Take note. Architects can do that. Just looking at the table. Okay? We can do that. So, what is your difference with them? So, you need to know how to do it manually. Understood? Critical stresses. Okay? The values are given for practical KL over R values of 0 to 200. So, there are so many tabulated values already. And for steels with FY 35, 36, 42, 46, 50. So 50 alone is the most used. 35. So the most used is 36 and 50. Okay. So maximum slenderness ratio. So the manual, the code does indicate that if KL over R is greater than 200, okay, the critical stress will be less than 6.3 KSI. So 200. So in the past, the AIC maximum permitted was 200. That value was based on engineering judgment, practical economics, and the fact that special care have to be taken. Take note. This is not mathematics. Okay? Take note. Engineering judgment, practical economics, there is no derivation of this formula or this relationship. Okay? Okay? But still, scientific. This is a scientific analysis. However, the analysis cannot be computed from those engineering aspects to the resulting final relationship or equation. Okay? So, as a result of this important practical considerations, the engineer applying 2010 code will probably select compression members with slenderness values below 200, except in certain special situations. For those special cases, both the fabricators and directors will be on the notice to use extra special care in handling the members. Okay? Maximum slenderness ratio, 200. Okay? In the past. So if you use that, FCR will be about 6.3 KSI. So example problems. So let us do the problems. Problem number 2. Using column critical stress values in table 4-22 of manual, determine LRFD design strength and is the allowable strength for the column shown in figure if 50 KSI is still used. Then letter B, repeat the same problem using table 4.1 of the manual. So let us compare the difference between table 4.22 and 4.1. Then letter C, calculate the design strength and allowable strength using equations of IIEC section E3. So this is the given figure. Okay, given figure. So compressive force. So section W12 by 72. So 15 feet. So maybe this is long column. So let us see if this is long column. So W12 by 72. So take a look at the values. 12 by 72. Where is 12 by 72? Let us look at table. 12 by 72. So we have here 12 by 72. Okay, so here we have 12 by 72. Okay, so this is 12 by 72. So what we need to get from the table are area, Rx, Ry, and D. Okay, so let's get those information. Area D and area and D is 21.1 and 12.3. Is that correct? So 21.1, correct. D is 12.3, correct. So we need Rx and Ry. So let's take a look at Rx, Ry. 72. Oh, this is 72. Okay, that is 72. Where is the Rx, Ry? So Rx is here. Ry is here. So Ry, Rx. So the third, 4, 3. 3, 4, 3. Okay. So 3, 4, 3. So this is Ry. Not that. The one above. 32.4. This one. Let us verify. Ry is not 32. So that's a wrong. It's a wrong value that we are looking at. This must be the value 3.04. Okay. So we are looking at the wrong value. 3.04. Okay. Okay. 3.04. And what about for Rx? 5.31. So here 5.31. So those are the correct value. 5.31 and 3.04. Okay. So we verified those values. Therefore, BF. We also need to find out BF, TF, K, and TW. So just look at the table. We have on the table. Okay, so here. So BF. So BF is in the above table here. So BF, TF, okay, and K, value of K. So K, this one. So let us proceed on 72. This is 72. Which column is first? BF, TF. So BF, TF. BF, TF. So let us go here. BFTF. So BF is 12. TF is 0.6. 7. BF is 12.67. Correct. K and TW. So let us take a look. Where is TW? Here. TW here. So and K here. So let us go. TW therefore is 0.43. Let's verify. TW is 4.43. And then what is the value of K? K is here. 1.27. K is 1.27. Correct. So everything we get from the table. So therefore, we can immediately find out B over T. That is what? 12 divide 2 because we are from the center, not from the edge to edge. Take note of this. So BF or the flange width is 12, but we have only to use half of that. So that's why 12 divided 2. 6 divided by 0.67. Okay? And that equals to 8.96, which is equal, greater than, less than square root of E over Fy times 0.56. So we have 13. So therefore less than. No, that is less than. So if that is less than, we are on the elastic. We are on the elastic side. Okay? Non-slender. Okay? Non-slender and stiffened flange element. So for non-slender, therefore let us calculate this one. Okay? H over TWs for the web. Okay? So let us look. H. So H is this one. This is total. So we are only using the edge from corner to corner. So that is D minus 2 times K. Just K is 1.27. So 12.3 minus 2 times K. So 12.3. We have to minus the 2 flange. The 2 flange dimension. Okay? So subtract the 2. So minus 2. Okay? So then divide by web thickness 0.43. So here 0.43. Therefore, you have 22.7. This is a very common number if you take the ratio. Very common number, 22.7. Very common number. Okay? So verify if this is less than 1.49 square root of E over Fy. So this is 35. Right? Okay? And therefore, it is less than. Therefore, it is non-slender stiffened web element. Okay? So, non-slender stiffened element. K is equal to 0.8 from table 5.1. Take note, table 5.1 here. Pin at the top, fixed at the bottom. That is 0.8. I think 0.7, but practical 0.8. Okay, so 0.7, then practical is 0.8. That's why here this author use 0.8. Okay, that is the reason why from table 5.1 that we showed a while ago. Then obviously KL over R. Okay? Take the computation, which is equal to what? K is 0.8. Then 12 times 15. So 12 is conversion factor. Then divide by R, which is 3.04. Okay? Then the result is 47. Okay? So using the same method, no? Using the same straight line interpolation, even though it is not 100% sure, use the interpolation. We do not have any other way. Okay? We do not have any other way. Okay? Then we can determine the design strength. Okay? Design strength is 38 because just multiply by 0.9. Multiply by 0.9. So we have this one. So here, divide by 1.67. So we have this value. Okay? So that is 1. And because of that, we can use the table. Okay? Table for 4-22 in the manual using FY is 50. Okay? So from the table, we can verify. So FCR, where's our FCR? Here. This one to this one. So 38.9 times area 21.1. Gross area. So here 21.1. That's our gross area. 21.1. So just multiply 21.1. So that is our design strength. So FCR multiplied by area divided by 1.67. So this is same as this 25 times 21.1. This is the allowable strength. Okay, using table 4-22. Okay. So take note, we interpolated in the table because we do not have the exact for this plural. So by interpolation, we have this answer from table 4-22. Okay. Letter B, table 4.1. So manual, meaning the code, says that KL is 0.8 times 15, that is 12. Okay. Then we have what? Design strength. Okay. From the table. So take a look at the table from 0 to 200. From 0 to 200, so there is a very thick table. So you can have this and verify. Compare that. So table 4-22, 805.8. Table 4.1, 807. So very near. There is a very near. Okay? So very near. 805, 807. Here, ASD method, 536.6. 537. So this is the same. This is equal. This is equal already. Okay. So what about letter C? Elastic critical buckling stress. So from part A is the what we calculated from A. Then Euler stress. So Euler stress. So you have the value 47.37 here. Then numerator, pi squared times E. So divide by that. So 137. This is equation 3-4. Okay. So now, compute equation 3-2 and 3-3. Now, let us find out if we are in 3-3 or 3-2. So, we already have this value, Euler. So, 4.71 square root of E over Fy. The value is 113. Because we have what? Fy is equal to 50. 113 for that. Okay. That is a constant. You can actually memorize this, 113.42. So, take note, we only have 47.37. Therefore, this is greater. Okay, this is greater. So, we are on inelastic. We are on the inelastic part. Equation 3-2. We are on the inelastic part. Therefore, we need to divide Fy divided by Fe. So, Fy divided by Fe. That is what? 50 divided by 127.55 here. That is the exponent. Exponent of what? 0.658. Exponent that, then multiply by Fy, then this is our FCR. So after finding out the FCR, we can therefore multiply by phi C, which is 0.9. So multiply by 0.9, so 38.19. And therefore, multiply by area, which is 21.1, 805.8. So the same. The same. So the answer for A, B, C, they are the same, essentially the same. Okay? So actually, this is the same in letter A. You can recall here. The answer in letter A, 805.8. So, here, 805.8. 805.8. The same. Okay, so any question? Let us move faster when explaining example 3. So, example 3, SSS, 16 by 16 by 1/2. This is the dimension and thickness is 1/2. Fy, 46 and the length is 18 feet. So, letter A, determine design strength, allowable strength with appropriate equation. We have the simple and support. Simple meaning pin. B, repeat A using table 4-4 in IIEC manual. Using table. So, letter A. So, get these values from the table. Then calculate B over T so that we can use the table. After finding this out, we can determine that it is K6. Okay? So, do this. I already showed you one by one the cases. There are 9 cases in table for B4.1a. Okay? B is approximated as tube size. So, 2 by T wall. So, B over T. So, again, use the value of K. So, 2 times 0.465. Okay? So, double that because top and bottom, then divide by 0.465. That is the thickness. Okay? Actually, this is the thickness. Divide, subtract the thickness. Okay? We are assuming corner to corner distance, that is for B. So, actually, the answer is 32.41. Is this less than this value, which is equal to 35? Yes. Therefore, the section has no slender element. Okay? There is no slender element. B over T ratio from table 1-12. Calculate KL over R. This is effective length. And FCR, pin connection, meaning simple. Support, so K is equal to 1. What is the ratio? Therefore, 1 L over R 1 over L over R, X and Y, compare. Which one is smaller? So the smaller one is 34.23. Okay? Is it less than this value? This value is 118. So, okay, less than. Use equation 3-2 for FCR. Therefore, first, find the Euler Strength. So, pi squared over pi squared times E divided by KL over R squared. So, therefore, we got this value. So, after this, divide 50 by this, not 50. Because the given is how much? The given is 46. So, 46 divided by that value. Okay? So, 46 divided by that value, you have this exponent. So, exponent of what? 0.658. That is constant. Multiplied by 46 because 46 our FY. So, equal to 42.51. So, if you have that, if CR, then you can multiply phi C, which is 0.9. So, the answer is 38. Then multiply by gross area, which is 28.3. Total. Design strength. For allowable, use omega 1.67. So, you have 720. Okay? Then, what about letter B? Using the table for the spore. Okay, just take a look at the table and you will notice the answer A and B the same. Okay, 1080, 1082. A matter of 2. That's why we are using what? 3 significant figure. Using 3 significant figure, 108. 1080. 1080. Okay? Oh, they are just the same. Same. Using the code table and computation using formula. Okay? Okay, so you can verify it by using formula and looking at the table. Any question? Let's have a question so that we can take a break and resume the discussion. So, I will not do example 4 anymore. Please do it yourself. Please do this. Very short. Example number 4. Okay. What? Determine the design and allowable strength for this figure, which is a built-up one. So, just what? The problem here is to determine the case. What is the case here? So, you have to use B from this point to this point. Okay? Okay, so that depends really on the shape of the section. So, that is a built-up section. And that is supposed to be welded because you cannot see any bolt. So, that is welded. So, then line by line, determine, find out how, what is the reason why it came from this line to this line. I am explaining you line to line by line. So, do it on your own so that we can take a break. So, and we will be back after, 1 hour? Back. So, please do this as your own activity, sample 4 and 5. Sample 4 and 5. And that's all about this column. So, we are through with column using the theoretical concept, using the code, using this textbook. So, there are plenty of things that we did talking about columns or actually loaded compressive members. Okay. Okay, you can also take a look at these problems. Okay, so we have covered all the chapter. Okay, so again, design, and chapter 6 is design. The chapter 5 is analysis. So design and analysis, particularly when they are with regards compression, they are just using the same formula and concept. So using the same formula and concept, as you can see here, very familiar values, very familiar formulas, very familiar table formulas. Okay, the only thing here is the procedure is inverted. Okay, so very familiar formulas here, very familiar. Already had this on chapter 5. So also using the tables. So, okay, also using the effective length. How this happened. So this is now L over 2, L over 2 for effective modified value. So ratio and proportion, using ratio and proportion. So just applying the lower mathematics, applying the lower math in this professional subject. Look at the equation. It's already familiar to us. We already know that. Those equations, we already know. This equation. Take a look. Okay. So, just a matter of so maybe this is a different discussion because we are what? Splicing. Splicing of column. Usually this is not done, but for very long columns, this is supposed to be the splicing method. So splicing method, just using the plate, using the plate, using plate and what? These are the symbol for welding. Plate and weld. Okay, welding. That is how, or using a smaller size column. So what? Telescopic type of what? Column. Okay, telescopic. So same concept, built-up columns, the same concept. We already know about that. Built-up columns with components in contact with each other. We already know that. Okay. Just consider this type, and this consideration is also the main topic of theory of structure. Okay, and strength of material. Okay, so if you know this type, okay, so you are very well prepared for the subject. Okay, this is the ideal in our case, but this is always there, explained in strength of material, mechanics of deformable bodies, theory of structure. Okay, so plates consisting of two plates connected to each other, reverse procedure. Okay, so we have intermediate connectors that are snug tight bolted. So okay, so can you see the type? This this is almost a Pythagorean theorem. This is a Pythagorean theorem, mathematics. Okay, Pythagorean theorem sa mathematics. Okay, okay. So, mathematics, you have to incorporate 1 and 2 sides. So, modified and then overall. So, just use the concept of Pythagorean theorem. Just Pythagorean theorem. Okay. Okay. So, that is only Pythagorean theorem, you know. Okay. Okay. Overall, modified. We are modifying it. Okay. So, what do we mean by A? So, this is what we mean by A. The distance between connectors. Okay. This is what we mean by A. Therefore, we can just choose Pythagorean theorem, connectors, and overall is equal to the modified. Okay. An example, as you can see, everything is a familiar formula. Okay. Oh, here is the Pythagorean theorem for the modified effective length over radius of gyration ratio. Okay. So, built-up columns, then problems on using the built-up columns. Trusses and lacings and perforated cover plates. So perforated, this means there are holes. There are holes like this. Perforated cover. Okay? That's what we mean by perforated. As you can see, so design really is just a matter of reversing the procedure when you are going to analyze it. So, very familiar. 1.4, we have 1.4, 1.56, 1.49. Okay, so those are the different cases, no? Different cases for coefficient and numerical coefficient here. Okay. So like this, case 6. So very familiar. So we already use that table. We already have example from the table. So there's nothing new about this. Just take a look if you have to. So those are the examples. So that's all with this type of sample and design. Okay. So okay, let's proceed to our break. Let's take a break. Any question? So let's have a break again. This is your professor, Dr. AP, preaching engineering for nation building.